Minecraft, it's a game about blocks. Strip everything down, you get this. A while ago I made this other thing. It's a robot that plays Minecraft, modded Minecraft. It needs debugging, and what better way to do that than simply creating our own dumbed down Minecraft. You can also check out the original video by clicking the thing up there. You should, it's literally a robot that plays Minecraft's hardest mod pack. What more can you want? Hey, it's me, God's chosen programmer, and today I'm going to tell you all about my Minecraft shaped test environment. So, I think that everyone here knows what a Minecraft is. What about a test environment? Well, a test environment is something very simple. It is something that tests code. There are many kinds of software bugs that you can't find by simply looking at the code. Even if you use an automatic tool like a linter, the code can still fail. The act of looking at the code by itself in an attempt to debug it is called static analysis. That means we are checking for bugs without running any of the code. The obvious counterpart, dynamic analysis, looks at the code while it's running. That seems much better. After all, the thing that actually does things is code that is running, not just a bunch of lines in a text file. So if we can find a way to analyze the code execution directly, then that's awesome. Unfortunately, the problem is exactly that. While static analysis tools only need to look at a bunch of unmoving lines, dynamic analysis needs to hook in directly with a bunch of fast-moving, always changing code. This is why that while static analysis tools work out of the box, dynamic tools always need a degree of custom fitting. Dynamic analysis is often done using tests, and the sandbox attracts these tests and gives them a way to talk with the code in execution is called a test environment. Here's how I'm going to subdivide this. We'll have 3 levels talking to each other. Level 1, the interface simulation. The mod we use for the robot is called Open Computers. Open Computers has a bunch of functions that allow us to interact with the Minecraft world. Things like move forward, mine a block, and stuff like that. Our code is constantly calling these functions, but they only exist within Minecraft. So we have to create fake, also known as virtual, versions of these functions that the code can actually call, while oblivious to the fact that it actually isn't running inside Minecraft. Okay, the robot calls move forward. Now what? We create a fake world and a fake robot. Here is the reasoning. When the robot calls a function, it expects something to change in the world around it. It called move forward, it expects to move forward. Called break a block, it expects for the block to break. So we need to write a whole lot of code to make that true. Not merely copying the function interfaces over, but also the expected results of these functions. This means, yes, simulated Minecraft, creating a fake version of Minecraft for our code to experience. Of course, that's a big deal. Well, I'll walk you over some of that code just as soon as I tell you about the monitoring layer. The thing is, we don't just want to simulate Minecraft, we want to run tests on a robot code as well. So we'll need a bunch of other code that manages this. We need code that allows us to simulate dozens, hundreds of different Minecraft worlds running experiments trying to break the code. And most importantly, we need to be able to track the progress of these simulations and detect if tests pass or fail. Of course, this is also very complex, with even more code magic required. Level 1 is the simplest level to implement. See these requires? They request code. Some of them request code that I wrote myself, some of them request code that is dependent on open computers. This code, obviously, does not exist outside of Minecraft, so that's what we need to change. We open up the Open Computers wiki and we start implementing the interfaces there. The wiki describes what a given function in a given module does and expects to receive as arguments, and we create a fake function that takes the same arguments and presumably does the same things. Some of it can even be copied directly from the Open Computers repository, with permission of course. But as you can see, in order to implement level 1, you must implement level 2. These dummy functions connect directly with the world simulation code. Just look at that. We request a block from the world that is in a given direction from the robot. But what does block, world and robot mean? Well, we need to code that in. This is a block. There is a bunch of data and callbacks here. There are render side things like color, which determines what color the block takes in the simulation, and a bunch of other stuff that actually defines what a block is. A certain item identity, being passable, being breakable by certain tools, etc. Things get really funky when we start messing around with stuff like custom behavior. You know, like saplings growing into trees or leaves decaying. What is an item? An item is two names. We can turn items into slots and slots into inventories, and then code a bunch of functions that define inventory manipulation, like taking items out and putting items in. The world is made out of a bunch of blocks, plus some other parameters. Most importantly, a robot that lives inside that world. A robot is something with a position, an inventory, and a bunch of possible behaviors. Wow! When we summarize things in a YouTube video like this, it almost feels like this was very simple to code. Now, level 3 is the funniest level. You might have noticed that the code so far was in Lua, but now look at this. It's C code. This is the rendering code. Ain't that cool? It's thanks to this bad boy that we can actually see what's happening. Okay, that's enough. As you know, Lua is an embeddable language. You can interact with C from it, and you can interact with it from C. That's what allows us to do this, to use a C library to handle the rendering, while the other logic connects directly with the Lua code. Raylib, cool library. And after we add a bunch of code in order to track variables, manage simulations, give starting conditions, and all that good stuff, we can actually start doing things. So, how does this look in practice? Remember the bug we had in the previous video? I can recreate it right here in simulation and show you exactly what failed. I set a goal condition for more than 20 saplings to be gathered. This was a mistake. I should have checked for goal completion or wood collected instead, but soon we shall see it doesn't matter.
It doesn't even matter.
I spawned in a large tree farm and a small tree farm, and I informed the robots that they exist, and place some wood and some saplings in the robot inventory, and then finally I tell her to go and do things. Alright, let's see you get stuck in a tree. Let's see that bug. Come on! Except that is not what happens. Somehow, the robot survives the gauntlet and is able to collect all the wood needed to progress to the next stage of the script. How? Well, turns out the bug is a bit more subtle than I originally thought. Here is an excerpt of my first diagnostic in the previous video.
It all seems normal, and then, boom, your robot suddenly bugs out while chopping down trees. Programming mega fans might have noticed that this is the most monkey-brained way of making this work. Since we don't track any state, and we simply execute the highest priority function pointer, when we try once again to execute the original task that was interrupted, kabloosh.
But here, the robot is not getting stuck inside the trees. But something quite similar is happening. See how it cuts across the chunk in order to get from building to building. This is not allowed. Rather, it should exit the building through a predetermined door position and then circle around the chunk into the other building. The fundamental bug is even more insidious than I originally thought. It is not simply that we are swapping tasks in a completely disorganized manner, but there's something more to that. Fortunately, thanks to our tooling, I found out precisely what part of the code is causing this. Bear with me for a bit. Every building has a set of high-level state variables. Let's take the oak tree farm as an example. Some of these variables are somewhat unique to this building type, like last checked and backhack. Others are required by a common building navigation system, FSM, which stands for Finite State Machine. In their structure definition, buildings utilize reserved symbols for navigation, asterisks, plus signs, and question marks. With this, we are able to order a robot to move to a specific position in the building, and from there execute arbitrary behavior, such as interacting with chests, machines, or even cutting down trees. This function, stdhook1, generalizes robot movement for any building. We start by checking if the robot isn't already inside the target building, or if the robot isn't inside the current chunk. If this is the case, then we use the nav2build module in order to navigate to the target building. This module's behavior is what makes it so the robot lives orderly through the door and circles around through the chunk edges into the target building. Anyway, after we confirm we are inside the building, we check the state of the FSM variable. Whenever we start using a building, it starts at 1, and then slowly increases as we move along it. Here is where the major bug lies. We check if relative navigation is set up. This is the module that controls movement inside the building. When we want to move somewhere, we set up a target coordinate and then execute the rel-move main function in order to slowly move towards those coordinates. The crucial thing is that if we are not set up, this is to say, if we have no current movement target, we'll execute the code inside this block. Here, in this line, we look at the building definition and check if there is a valid unvisited question mark location to path towards. If there isn't, which is the case for the oak tree farm building, we'll set FSM to 2 and return early, from where we'll attempt to move to a yet unvisited asterisk location. But here is the bug. What if we task switch from working on oak tree farm to small tree farm while we are in the middle of moving around? The rel move function will still be in a setup state, so it will skip this check and start executing an old movement instruction. But this still doesn't explain the getting stuck in trees part of the original bug. After all, the robot should still be moving towards a valid target, even if it is doing so at the wrong place in the code. Haha! But now we know that movement orders are not getting marked as closed properly, in addition to the robot's task switching being poorly programmed and poorly thought out. But then, what was causing the original bug? It is right here in nav2build. The robot switches tasks while on top of the tree, and nav2build detects that we are in a different chunk in relation to the target building, and it attempts to chunk move. The problem is that chunk move doesn't know that the robot is inside a tree, and so it attempts to move forward as if there were no leaves there, and so it gets stuck. Mystery solved. This is going to need a full rewrite, isn't it? So, that's a test for you. Kinda cool, huh? With the help of this, I debug things much faster. Make sure to check out that first video if you haven't already, and get ready for the videos to come. The GTNH video will still take a good while to come out, but until then, I'll be posting some other things. Maybe more programming videos, or who knows. I'll find something else interesting to talk about, or maybe the sequel to one of my artistic videos will come out. Well, the sky is the limit, so make sure you're here to witness it. Bye-bye!